I want to mention that so far we worked on two big families of discretization orders. In the first family of discretization orders, we have the so-called consecutivity assumption satisfied. What it means? It means that for every reference vertex, let's say I, my reference vertices are the ones that immediately precede I. So in this case, in dimension 3, if when I'm on the vertex I, my reference vertices will be I minus 1, I minus 2, and I minus 3. In the other case, we don't have the consecutivity assumption. And in this case, every vertex from the first to the one ranked I minus 1 can be a reference vertex. So for example, in dimension 3, over there we have the example when we have the consecutivity assumption. And in this case, the simplex inequalities for the reference atoms, if you want, in this case, the triangular inequality, must be satisfied there. So we have a precise window where the triangular inequality must be satisfied strictly. In this case, we have more freedom, and so the simplex inequality must be satisfied on the simplex defined by the subset of reference atoms. This atom, for instance, is in the middle here, but it's not considered the construction of the simplex. So why two big families of the discretization orders? Okay, there are many reasons that are related to the consecutivity assumption that I just mentioned to you. And now with colors, with the blue and the red, I will mark the reasons that were in favor to the consecutivity assumption and the motivations that were against this consecutivity assumption. So in favor, in blue, historical reasons. So we started with this. So all our first papers related to orders consider the consecutivity assumption because we started with this kind of orders. And then second, especially this man here in the first row that gave the presentation before me, he was used to handcraft discretization orders. Because when you have a protein, for instance, which is our main focus, you know the chemical structure of the protein. So you know that the C-alpha carbon atom is bonded chemically to this nitrogen. So you know that there is this H in the graph, and it will be in all graphs related to proteins. And so you know something that you can exploit for constructing an order that can be valid for any kind of instances for the same class of problems. And when he was doing this, he was checking the current atom I and the three immediate preceding atoms. So he had the consecutivity assumption. Then, when you have the consecutivity assumption, like Lilia mentioned also to this, you have the symmetry properties on the trees defined on these trees that become our search domain. And when we don't have the consecutivity assumption, we lose this symmetry property. Of course, as you also mentioned, we can exploit these symmetry properties to speed up the algorithm. But in the case in which all the distances are exact, when we talk about proteins, we have many intervals. So we lose this property, but we cannot really exploit this property when we have the algorithm. Now we have this line where I put two colors, because if you really want to intersect the spheres in the practice, you start with the equations, then you go you define a system of quadratic equations. Then there is somebody that proved that this equation, if this equation has this system as solutions, can be found by solving two linear systems, one nested in the other. But if you do this, you have in the practice, if you implement this in C and use Lama, for instance, for the linear systems, you have numerical instabilities. So for many years we used another method that is, I will not go into details, but I will tell you that it's based on the multiplication of 4x4 matrices. So much more stable than solving a quadratic system. And but this method required the consecutivity assumption. So for many years we considered orders with the consecutive assumptions also for this reason, until very recently when one of our students, that is now in Reno making a postdoc, he found a way to generalize this method to any kind of order. So finally we are able to solve with the same precision, with the same accuracy, also instances where the order is an order without a consecutivity assumption. Finally, completely read, I have a method for detecting automatically the discretization orders. So why this is completely read? Because if I want to formulate a problem, I have the graph G, I want to find the discretization order.
Suppose